Hello. According to the last reading assignment, the reading assignment was about set theory and functions. So far, we did set theory, and today I want to outline the ideas in the functions part of the reading assignment. So let's define what is a function. A function is an object which is like a relation between two sets. A function f defined on a set A with values in a set B. So this is called a function from A to B. Function from A to B. A and B are sets. The designation for the set A is the domain of the function, and the set B is called the codomain of the function. So, in short, that's how I denote a function. Function defined on a domain A with values in the codomain B. Function f from A to B. What's the meaning of this? Meaning. So think about this diagram. Imagine on the left, we get the set A. On the right, we get the set B. The set A is a bunch of elements, right? And the set B also has a bunch of other elements on the set B. So we can imagine a function as a set of arrows emerging from the elements of the codomain. So to each element of the domain, we associate exactly one element of the codomain. So in other words, the picture shows that from each element of the domain A, there is exactly one arrow pointing towards an element in the codomain. So we can do this, we can do this, and I don't know, make a choice. We can do the same, right? So let's label those elements. Let's see A, B, C, D, and here we can label them 1, 2, 3, 4, and 5. So how do you read this diagram? F of A equals to 3. F of B equals to 4. F of C equals to 1. And finally, F of D equals to 4. So that's a function. So to each element of the domain, we associate exactly one element of the codomain. So okay, so that's one possibility, one way to introduce the functions. So let's define categories of functions. It will be useful for the homework, right? We get one-to-one functions. So a function f from A to B is one-to-one. We can abbreviate this by saying 1-1. Is a function one. The function f is 1-to-1 if different elements in the domain are mapped into different elements of the codomain. If for every x1 and x2 in A, right, if x1 is not equal to x2, then f of x1 is not equal to f of x2. That's the formal definition of the one-to-one function. This like reverted A is for every, reads for every. It's called a quantifier. For every x1 and x2 in A, if x1 is not equal to x2, then f of x1 not equal to f of x2. So the picture is like this. Let's think about the diagram back. This is A, this is B. So for every x1 and x2, we can get an x1 here, an x2 here. If they are different, then they are mapped different elements of the codomain. So this is f of x1, this is f of x2. And one-to-one means that if x1 is not equal to x2, then these two are are different as well. So if x1 is not equal to x2, then f of x1 is not equal to f of x2. So what is the counterexample? What should not happen so that the function is one-to-one. So let's do a defeater for one-to-one in a sense. Defeater for one-to-one. In the sense that if we see this defeater, the function is not one-to-one. If you don't see this defeater, the function is one-to-one, if it's a function, right? So let's see. This is A, this is B. A defeater will be something like this. X1 and X2, different numbers in the domain, are mapped to the same elements in the codomain. That's a defeater. So in this case, f of x1 equals to f of x2. So if we see this, then the function is not one-to-one. That's why it's called a defeater. If we see this pattern like a V shape is a defeater as shown in here. This V shape is a defeater for one-to-one. So if you see this V shape, the function is not one-to-one. If we don't see this V shape and it's a function, then the function is one-to-one. So let's try to give an example in which we apply this defeater. Exercise. Let f a function from R to R, real numbers to real numbers. F of x equals to x cubed minus x plus 1. Can we show that? So prove that it's not one-to-one. Prove that f is not one-to-one. Well, so solution for the solution, we have to provide a defeater, a V shape. It's a V shape. So in other words, you have to give me an example of two different elements, x1 not equal to x2, but f of x1 equals to f of x2. So this will be 0, 0, and 1. So what will be f of 0? F of 0 equals to 0 cubed minus 0 plus 1 equals to 1. F of 1 equals to 1 cubed minus 1 plus 1. This is 0 and is still 1. So in other words, 0 is not 1, but both f of 0 and f of 1 are 1. So it's a V shape, which is a defeater for one-to-one. So we just proved that this function from R to R, real numbers to real numbers, given by the formula x cubed minus x plus 1, is one-to-one. Okay, so this is one category of functions. Another important category of functions is onto functions. Just to clarify the essence of the materials in the reading assignment, onto functions. So a function is onto if every element in the codomain is in terms of those images is hit by some arrow emerging from the domain. So this is an onto function. So this is clearly not one-to-one because we have a defeater, not one-to-one, but every element, this is the domain A, that's the codomain B. So every y belonging to the codomain is of the form f of x for some x in the domain. Is of the form y equals to f of x for some x in A. So let's put based on this idea, let's put a formal definition. So f from A to B is onto if for every y in B in the codomain, there exists an x in A. So for every, so this sign is for every universal quantifier. For every y in B, this reverted image, there exists the meaning of the formulas here. So for every y in B, there is an x in A such that f of x equals to y. So that's a formal definition of onto functions. So in other words, every element of B is targeted by an arrow emerging from A. Okay, so what would be a defeater for onto? Just because it's easier to understand. Sometimes it's easier to understand concepts by using defeaters. So what does mean not onto? Not onto. Not onto means there are isolated elements in B which are not hit by any arrow. Isolated elements in B in the sense that not hit by any arrow emerging from the domain. So not hit by any arrow emerging from the domains. For example, this function is easily not onto. So this is a function. So this is A consists only of one element. B consists of two elements. So that's a function, of course, is one-to-one because there is no V shape like this. So like different elements of domain targeting the same element in the codomain, and is not onto because this is not true. It is not true that for every y in B there is an x in A with f of x equals to y, because for this y, isolated y, there is no x in A such that f of x equals to this y. So not onto. Okay, so far we know what are, let me summarize, what are one-to-one and onto functions. So far, let's summarize. One-to-one means no, there's a quickest way to define them. No V shape like this. Right. Onto means no isolated point in B, right? No isolated point in the codomain, right? So this one-to-one and onto. So one-to-one means no V shape. Onto means everything in the codomain is taken. Let's combine these two concepts, one-to-one and onto. That's called a bijective function. So bijective function equals one-to-one and onto. This idea of bijective function. So here's an example. So as a rule of thumb, if you talk about finite sets, every bijective function from a domain A to a codomain B, or if a bijective function exists, the number of elements in the domain must be the same as the number of elements in the codomain. So let's say we got 4 elements in the domain, 4 elements in the codomain, and this will be a one-to-one and onto. So let's label the elements. We can say, I don't know, 1, 2, 3, 4, that's 8. B is 5, 6, 7, 8. So this function f from A to B, this is the function f from A to B, is one-to-one, means no V shape. And onto, no isolated elements in B. No isolated elements. Isolated in the sense that not targeted by any arrow. So one-to-one and onto, right? What's so specific about, what's so important about bijective function? Bijective function is a function which are invertible. What does it mean invertible? We can reverse the arrows to get a function from B to A. So let me use another color to indicate what happens if we reverse the arrows in this diagram. This happens for a bijective function. We can reverse the arrows and we still get a function from B to A, which is called the inverse function. So reverse this arrow, 6 will be mapped into 1. let's reverse the arrows and do the reverses in blue. Reverse this arrow, 8 will be mapped into 2, and reverse this arrow, 7 will be mapped into 4. So reversing the arrows produces a function from B to A, which I'll denote in blue. From B to A, the notation is F, like f to the power minus 1, but don't confuse with 1 over f arithmetic, the inverse of a real number. It's the inverse of a function, f inverse from B to A. So in other words, so look at one of those arrows, f of 1, right in white, we do f of 1 equals to 6. And if we reverse, write it in blue, if we reverse the arrow, f inverse will go back. So if f of 1, so via f, 1 goes into 6, via f inverse, 6 will go back to 1. So f inverse of 6 equals to 1. So the inverse reverses the arrows. So for the inverse, reverse the arrows. If possible. If it's not possible, then for a random function, reverse the arrows, we don't even get a function from B to A. For the inverse, we reverse the arrows. So for example, if a function is, let me give an example. So that's a function from A to B. Of course, a function from A to B, but in white. This is A. This is B. This is F. But if we reverse the arrows, this is not a function, because if we want to reverse the arrows to these elements in B, we associate 2 elements in A, so this cannot possibly be a function. So reversing the arrows will not produce a function, but we'll see later it will produce a relation, but not a function. So it is impossible to reverse the arrows and get a function from B to A. So that function is not invertible because, first of all, the function is not one-to-one. To be invertible, the function must be both one-to-one and onto. A typical problem here, and with this I'll finish this summary of the reading assignment, is how to find explicitly the inverse of a function. Right? So procedure to find F inverse. So here's an example which is similar to an example which is in the homework. Right? So let F be, I don't know, let's put it here like minus infinity 3 with values in to infinity. So this is the domain, is the codomain. Domain is minus infinity 3, the interval minus infinity to 3 included. The codomain is to infinity. So f of x equals to, let me give a formula, x squared minus 6x plus 11. So is f invertible? If it is, find the formula for the inverse. So I'll describe a shortcut to find the inverse right away. Is f invertible? If it is, so if so, find f inverse. A typical problem. So what's the idea here? If we have a direct function, then there's a domain, there's a codomain. Right. This is x, this will be y. And if the inverse means we reverse the arrows, right? The blue, white blue here. So there's the function f maps x to y via f. And if we reverse the arrows, f inverse will map y into x. That's f inverse. So how do you read this? If f of x equals to y, then x will be f inverse of y. So that's the idea which will ring in our minds from this moment on. To find the inverse, what is f inverse of y? We have to solve for x. So once we get the f of x equals to this one, we can call this y. Solve for x. If we manage to solve for x in terms of y, so if we look at the normal function, we get y in terms of x. Y in terms of x. In terms of x. That's the normal function, f of x equals to y. Read it, y equals to something, y in terms of x. For the inverse, try to solve for x in terms of y. If we can do this uniquely, so if we can solve uniquely for x in terms of y, if we can always solve uniquely for x in terms of y, we got the inverse. We got x equals to f inverse of y. So we got f inverse of y equals to whatever it is. And that's the idea before starting to solve this problem. We have to, that our objective is to solve uniquely for x in terms of y. Okay, so let's start. So let's start the solution based on this idea. Start with f of x equals to y. Start with f of x equals to y. Let's see what we get here. F of x is x squared minus 6x plus 11 equals to y. But once we write this one, so we have to write down exactly the specifications. Where is x living and where is y living? So this is, the domain is x is for the domain and y is for the full domain. Right? So what can I say about x? X is less than or equal to 3. It's very important to write down those specifications. What about y? Y lives here in the codomain. So y is bigger than or equal to 2 because 2 infinity means all the numbers, all the real numbers bigger than or equal to 2. So y is bigger than or equal to 2. That's very important to have all of this written down to start with. Okay, so now we have to solve for x. We have to make sure that to prove that the function is invertible, the solution for x must be unique. So let's rewrite this as a quadratic equation. So x squared minus 6x plus equals plus 11 minus y equals to 0. Okay, so what will be, so let's use the quadratic formula. X1 comma 2 equals to 6 plus minus square root of quadratic formula 36 minus 4 times 1 times 11 minus y. So minus 4 times 11 is minus 44 plus 4y if you do minus 4ac divided by 2a divided by 2. So in other words, x1 comma 2 equals to 6 plus minus square root of 4y minus 4y minus 8. 4y minus 8 divided by 2. And if we divide by 2, both terms here, 6 plus minus, so 6 divided by 2 plus minus square root divided by 2. To divide the square root by 2, we'll divide inside the square root by 4. So this will be 6 plus minus, no, sorry, 3 plus minus, we'll divide 6 divided by 2. 3 plus minus, the square root divided by 2 means inside the square root divided by 4, square root of y minus 2. So let me continue here. So we got two potential candidates. We only need one solution because we need to prove the function is bijective, we need exactly one x. So to x to solve uniquely. So x1 comma 2 equals to 3 plus minus square root of y minus 2. So at least one solution exists, but not two solutions. Right. So in any case, look at the specifications. Y is bigger or equal to 2. So since y is big, since look at the observation here. since y is bigger than or equal to 2, the radical exists, very important. Since if y will not be bigger than or equal to 2, we'll get imaginary numbers out for the due to the radical. So not good. So that's important. So we made use of this, right? It's necessary to y to be bigger than or equal to 2 in order for this radical to be. Otherwise, there is no solution, right? So we are good now. Now we are looking for 3. X is bigger than or equal, smaller than 3. For x to be smaller than 3, a radical is always bigger than or equal to 0. So for example, radical of 4 is 2, not minus 2. So for x to be more than 3, we have to choose minus. For x more than 3, must choose the minus sign. Because in 3 minus more than or equal to 3. So instead of x1, 2, we get only one x. So x, which is unique, is 3 minus square root of 1 minus 2. And this we managed to solve uniquely for x. So we managed to solve uniquely for x. We managed to solve uniquely for x. Therefore, the function is invertible. So therefore, f is invertible. And let's write down the conclusion. So, okay, so let's put it. Okay, so I will erase this. I keep the fruit of the work. I erase the work. So we know the f is invertible. We got x in terms of y. So what can we formulate the conclusion? F inverse. The inverse goes from the domain of the inverse is the codomain of the function, and the codomain of the inverse is the domain of the function. So f inverse goes back from 2 infinity. Very important. We must write this stuff from 2 infinity with values in minus infinity 3. From 2 infinity to minus infinity 3, f inverse of y equals to 3 minus square root of 1 minus 2. In any case, the naming of the variable is immaterial, so it doesn't really matter. We can say, so, or we can say f inverse of x. At this moment, x is dead, so there is no more reference. X is something like a random variable, like an arbitrary naming of the variable. So f inverse of anything you want. So f inverse of like a rhombus here equals to 3 minus square root of rhombus minus 2. Or f inverse of x equals to 3 minus square root of x minus 2. Doesn't really matter. So, but if you want, you can keep it like this. F inverse of y as a result of this problem is 3 minus square root of y minus 2, which is x obtained in terms of y uniquely. This is x, which is f inverse of y. X as a result of this problem was obtained in terms of y uniquely, right? Okay, then. So this kind of covers the functions part of the reading assignment of set theory and functions. Another part which probably I'll do it here is I give you a problem which will prove a set identity by using first membership tables like Boolean tables or truth tables or Venn diagrams. Let's do a Venn diagram here. Proving set identities. We did it by membership tables. We already done, this already done on the previous lecture. But also, let me, because it's a homework, let's do Venn diagrams. So, okay, so let's see. Let's try a set identity like A minus B union C equals to A minus B intersected with A minus C. Let's prove by Venn diagram. Okay, so we have three sets A, B, C, right? So let's do first a Venn diagram for the left-hand side. Let's call this left-hand side. And let's call this right-hand side. Let's do a Venn diagram for the left-hand side. This is the universal set. And this universal set, write down the sets A, B, C, so that all pairwise intersections show up. This is A, this is B, this is C. Okay, so A minus B, parenthesis P union with C. P union with C is this one. A minus B union with C is whatever is in A but not in B union with C. So that will be this one. That's the result of the left-hand side, A minus B union with C. So this is the result of the left-hand side. Okay, let's do the right-hand side. There's the left-hand side. Same sets. All pairwise intersections must show like the Olympic circles if you want. So this is A, B, and C. Okay, so now we got A minus B. Whatever is in A but not in B. In A, not in B. This is A minus B. A minus B is this one. A minus B. Now let's use another color. Let's put A minus C. Whatever is in A and not in C. We're in A, not in C. In A, not in C. Now we have to intersect. So the green area with the white area here, the intersection will be exactly the same with where you see both white and green here. White and green. Now, if you look at there's the Venn diagram for the right-hand side. And look at the diagram. So what is the visualization of the left-hand side is this part, this area. Visualization of the right-hand side is the same, like a geographical region. Okay, so this guys kind of concludes the reading material on set theory of functions. Okay then. So I'll see you tomorrow. Tomorrow we'll move on because there is no time. We'll do number theory and cryptography. Okay, so I'll see you tomorrow then.